linear approximation and differentials. Okay, so here's the situation here. Just looking for my ruler. Okay. So imagine I have a function so here's a function f, okay, and at a certain point here, point, let's say a, x is a, this of course is f of a. Okay. Well, I have, of course, a tangent line. Okay, so this is what we've been doing until now. Okay. And as, of course, this, we know how to find the slope. Okay. And so also we know how to find the equation. Okay. So the equation of this line, of this tangent, okay, I'm going to call it y equals L of x. That's the equation of this line. Okay. So the equation of the tangent line. Okay. And we're going to use this line to approximate the curve, to approximate the function. Okay. So, of course, we're way off, but if we're trying to find the value of the function at a value x close to a, that could be a good approximation. Okay, if you look carefully, okay, so if I take a value here, x, okay, well, there's going to be two values, this and this. So this value here, well, this will be point x f of x, and this value here will be x and L of x. Okay, so of course they're off, but it's not that bad. It's a valid approximation, of course, provided that x is close to a. The closer x is to a, the better the approximation. Of course, as you see, if I take x here, right, then you see that you're a bit less off. Do you understand? Is this clear? It's much better when I see faces. Yeah, it's better. You good? You get it? Rebecca, you see, I don't think that you get it. Yeah? Okay.
Yeah, I get it.
Okay, good. So let's write down the definition here. Okay, so L of x is called the linear approximation okay, or the linearization of f at a. Okay, so it's very complicated word to express just the equation of the tangent line. That's what it is. The equation of the tangent line, that's what it is. Okay, what's important is that at a. Okay, so of course, if a was somewhere else, you would have a different L of x. Okay, so let's find the equation of this line. So now we're looking for the equation of this line. Okay, so what is L of x? Okay, so of course, I'm looking for the equation of the red tangent here. I need two things. I need to find the equation of the line. We know we need a point and the slope. Okay, so we have a point. Which is, of course, a f of a. That's one thing we have. And also we have a slope. What is the slope? What is the slope?
F prime of a.
Very good. F prime of a. Perfect. So we could find now the equation of the red line. Okay, so let me just draw it here like this. Okay, so let's say this is my, oh, I know what, I'm going to draw it in red so that you understand when you're at home that I'm talking about the tangent line. So we draw the exact same line here. Okay, so I have a point here, which is a f of a. Okay, let's say I have a random point on the line x, y, and I have the slope. The slope here is, we know, f prime of a. Okay, so I have everything I need to find the equation of the line. So the slope between any point xy and af of a should be f prime of a. So I'm gonna write this down, right? So I'm gonna write like this. So for xy to be on the line y equals L of x, okay, we must have, well, the slope, so y minus f of a, right? y2 minus y1 over x2 minus x1, which is x minus a, has to equal to the slope.
Sorry, can you move your paper down, please?
Oh yeah, thank you. Okay, so again, I repeat since it was cut off. So for a point xy to be on the line, well, if you take the slope between these 2 points, it needs to give you f of a. Okay, because if I take xy here and I do the slope, I will not get f prime of a. So that means that this is not on the line. That's what it means. Okay, the fact that the slope is f prime of a guarantees that xy is on my line. And that's what I wrote here. Good. It's a very important way to look at it because you're gonna use this a lot in linear algebra. And that's it. So now I could find the equation of the line by just isolating y. Okay, and so y minus f of a is equal to f prime of a times x minus a, and so y is equal to f prime of a times x minus a plus f of a. Okay, this equation here, this line, is what we call big L of x. Okay, so I'm gonna write it here. So big L of x is equal to f prime of a times x minus a plus f of a. Done. This is important. This is what we're going to use as a linear approximation. Okay, so it's the first step, it's the beginning to what we call Taylor polynomials, which you will do in calculus 2. And if we have time by the end of the course, I could introduce you Taylor polynomials as well. Do you have any questions?
So now we just calculated the simple, what's it called, tangent line.
I just calculated the simple tangent line, exactly. Okay, so let's put some numbers into this because this is theoretical. Okay, very nice. This is what you need to understand. Well, this is what you need to remember, but you need to understand this idea. Okay, does anybody want me to repeat all the logic here? Okay, we're almost done. That's it. That's almost all there is. I'm going to do 1 or 2 examples, and that's it. We're going to pass to the next subject. Okay, so any questions on this?
How is this any different from like a regular tangent line? Like, why do you say a simple tangent line?
It's not different. It's not different at all. It is a tangent line, except that now, since we're at the part of the course where we're in applications, so let's see. Until now, we've been finding tangents, and then what's it used for? What's the purpose of this? Okay, you always, every student as the teachers, what is this for in life? You know this question. I've been getting this maybe hundreds of times. Well, now that's what we're doing. The rest of the course is what is this for in life? Okay, so here, we're going to find an application. So what's the use of this, of finding this tangent line? That's what I'm saying. Okay, and so one way to look at it is to approximate a function, and you will see why. Okay. So let me give you an example. Example pen. Okay, so example. Let f of x is equal to the square root of x minus 1. Okay, so 2 questions. 1, find the, I'll write it in long, linearization of f at a equals 5, first question. And second question, use Lx, so the linearization, to approximate two values. So a, let's say the square root of 1.98, and b, the square root of, no, sorry, not 1.98, sorry, 3.98, sorry, 3.98, and the square root of 4.03.
Is f prime of a 0?
Excuse me?
Is f prime of a 0?
F prime of a? Yes,
Yeah.
F prime of a, no, it's not 0. F prime of a, you do f prime of x, and then you plug in a.
Oh, okay.
Okay, it's not f of a prime. It's not the same thing. Okay, so let's do this. So the first thing is I'm going to find a linearization. So just a reminder, L of x will be equal to f prime of a, which is 5, times x minus 5 times f of 5, plus f of 5, sorry. Okay, this is what I'm looking for, this equation here. So f of 5 I could calculate. I just need to find f prime of 5, and I'll be good. You with me? Anybody? Okay, so let's go. I need f prime of x. So f prime of x is, so we know the derivative now. How to find this? 1 over 2 square root of x minus 1. And so f prime of 5 equals, I just plug in 5 in here. 5 minus 1 is 4, square root of 4 is 2, 2 times 2 is 4, 1/4. Question? Okay, good. Alexandra, you get it? Yeah, you get it? Yeah, okay. All right. And what's f of a? F of 5, sorry, because I'm going to need f of 5 here. So f of 5 is, of course, you plug in 5 here, you get the square root of 5 minus 1, which is going to be 2. So now I have everything I need. I have this value, I have this value. I could now find the equation of the tangent line. Okay, so big L of x is equal to f prime of 5, which is 1/4, times x minus 5 plus f of 5, which is 2. This is my answer to my first question.
So what does it mean? Every time any x that we plug in, it's going to give us the tangent line.
Yeah, exactly. Any x will give you a y on the tangent line. Exactly.
But
Okay.
I have a question.
Yeah, sure, go ahead.
Like, weren't we doing this before, just like not with the equation?
Yes, but we weren't using it to estimate a function. Okay, so now I'm going to use this to estimate a function. So what I'm saying, basically, what I'm saying, so what, I'm going to write this in English, what we are saying is that if x is close to 5, okay, then the square root, so f by function, which is square root of x minus 1, is a good it could be approximated nicely by this. That's what we're saying. You get it? You get it?
Yes, thank you.
Okay, so now I could use this to answer the second part now. Okay, so I'm looking for the square root of 3.98. Okay, so this is equal to the square root of, well, 4.98 minus 1. Okay, because I just want to have it in this form. That's my x.
Where'd you get the 4.98 from?
because I'm looking for the square root of 3.98.
Yeah.
So 3.98 must be equal to the x minus 1. So the x has to be 4.98. Yeah. So that I get 3.98 inside the root.
Oh, okay.
Okay. So that's my x. So this is approximately equal to what? Well, I'm just going to use this now. 1/4 times the x, which is 4.98 minus 5 plus 2. So again, this is my x. And now I could calculate this. Are you with me? Oh, I'm going to move up, sorry. Okay, so let's estimate. So 4.98, I don't know if you can see. There you go. 4.98 minus 5, I get this, times 1/4, so divided by 4, I get this, and then plus 2. So I get 1.995. This is what I get as an estimation of the square root of 3.98. Okay, let's find the exact value. So exact value. So let's do 3.98 square root. There you go. You see what I get? I get 1.99499. Well, that's not bad.
Sir,
Yeah,
sorry, could you repeat the part where you did the square root of 4.98 minus 1 because my Wi-Fi cut out?
sure. So how did I get this here? Where is this from? That's what you're asking?
Yeah.
Okay, because my question asks me to estimate, sorry, I'll move up, to estimate the square root of 3.98. Okay, so my function is what? It's the square root of x minus 1. So I want to make sure that x minus 1 is 3.98. So the x needs to be 4.98. You understand?
So it's always going to be plus 1.
It's always going to be, in this case, for this function, there's different functions.
Oh, yeah. Okay.
Okay, but I have to make sure that what's here is exactly what's here. So what should the x be for this to be equal to that? Get it? Okay. So what we just did is pretty good because we used a linear function. So basically linear operations, just multiplying, adding, and dividing to find a square root. That's not bad. I guess that's how they would do in the old days if they wanted to find the square root of a weird number. How would you find this if you don't have a calculator? You have to try and error. Well, this way, you could just estimate it with a linear function and choose your x smartly enough, and you could find your square root. You understand? Okay, try the second one. Okay, so that was A. It's A. Let's try B. Okay, so the square root of 4.03 is equal to the square root of 5.03 minus 1, which is approximately equal to 1/4 times 5.03 minus 5 plus 2. And so I get, so 0.03 divided by 4 plus 2. So I get 2.0075. Is this what you get? Okay, and so let's find the exact value. So let's do the square root of 4.03. So 4.03 square root, there you go. I get 2.007486. Not bad. Okay, we're off to the 1, 2, 3, 4th decimal. Okay, are there any questions?
So just to make sure, the L of x is the equation of the tangent line, right?
Yeah, exactly.
But can't you just find the equation of the tangent line using like f of x and a?
Yeah, same thing. I just added one information. I give you the name of that tangent line. That's all. Okay, the tangent line at a certain point is called the linearization of the function at that point. That's it.
Okay, so we just do it differently in this case.
Okay, same thing. Okay, can I move on? Anybody have questions? Okay, so this, I think this is pretty easy now. That's okay. Let's go with differentials. Okay, so let's let y equals f of x be a differentiable function. Okay, so basically a function for which you could derive. We're going to talk about this a bit later. Okay, then so we call the differential dx, okay, is an independent variable I'm going to explain everything I'm writing in a minute. And the differential y is defined as, okay, so dy is equal to f prime of x times dx. Okay, so let me finish writing and I'm going to explain to you. Okay, so this means if I increase my x by something very, very, very small, by how much does the y increase? Okay, a small value, a small increase of x causes a very small increase of y. By what factor? And that's the factor which is f prime of x. Okay, let me give you an example and you're going to understand it with the example. Okay, it's an example I took from the book. Okay, so the radius of a sphere is 21 centimeters with a possible error of at most 0.05 centimeters. Okay, so the question is, what is the maximum error in using this error to compute the volume of the sphere? Okay, so this is the wording of the book. But what the student wants is the following. Okay, so finish writing. Okay, so I have two. So I have one sphere, and there is an error here in the radius. They're telling you there's an error here of, I'm going to call this dx. This is the error in radius. So you know what? I'm going to call this. I'm not going to call this r. I'm going to call this. No, I'm going to call it. I'm going to call it r, and I'm going to call this dr. Radius r and dr, which is the error, the small increase in radius. So I want to know a small increase in radius will give me an increase of how much in the volume. Basically, that's the question they're asking. Okay, so let me write down what's given. They give me that the radius is 21. They're giving me that dr is 0.05. And I'm looking for dv. Do you get it? All right, so let's find what is V, what is the volume of a sphere, 4/3 pi r cubed. And so dV dr, the derivative of V with respect to r, is equal to, so I want to derive this, 4/3 pi 3r squared. And so dV is 4 pi r squared times dr. And I have everything now. I could calculate dV. 4 pi 21 squared, 0.05. I get 21 squared. I'm just multiplying it. I get 277.09 centimeters cubed. This is what the increase in volume will be. Is there questions?
I'm not sure if you said it, but where did you get the 4/3?
Where did I get, sorry, what?
The 4/3.
Oh, this is the volume of a sphere. That's how you find the volume of a sphere.
Okay, thank you.
Okay.
How do you pass from the cube to the square from the first to the second step?
From here to here,
Yeah, exactly.
I did the derivative. I'm doing the derivative. I'm doing v prime. So that's a constant. How do you find the derivative of x3? It's 3x2.
Oh, yeah, okay, thank you.
Okay. Okay, another example. You done?
Sir,
Yeah.
can you just explain why we have to take the derivative to find the maximum error?
Because they're telling you here that this is, at most, that's the maximum error in the radius. So that will cause a maximum error in the volume. Do you understand that?
Yeah.
And so for this error in radius, what is the change in volume? Basically, that's what they're asking. Okay. If you want, you could find the volume of the sphere with 21 centimeters squared, with 21 centimeters, and then find the volume of the sphere with 21.05, and minus the two volumes, you should get something closer to 277 as well.
Okay. But I just don't understand why, if you take the derivative, why it works.
Why it works? Because what we're doing here is the same as before. We're doing an approximation of this function with a straight line at point 21 and whatever the volume is. It's exactly like what we did before. Okay, don't forget that a slope is a rate of change. Okay, so it's a rate of change. So if you want, if I were to maybe try to express what we have here, maybe I'll fit it here. I'll do it on the next page. One second. Okay, so that you see what's going on here. Okay. So let's say I have a function like this. Okay, so it's always good to, maybe I should have done this before and illustrate it graphically. Okay, so let's say I have a function like this. I don't know, let's say, okay. So this is a function f Who cares? Okay. And then I have a point here at P. Here, X. Okay. And I'm going to go a bit further here. Let's say X plus delta X. Okay. So this here is delta X later. Okay. And I'm going to go like this. Okay. Point P. And then I'm going to draw my tangent here. Okay, this is my linearization like before. Okay, and so this distance here, this was my dx. This is my dx or my delta x. Okay, dx or delta x, same thing. It's what the small increase in dx. Okay, so a small increase in dx generates in my function here a small increase in the y. So this is called delta y. Are you okay so far?
Yes.
Okay. So now, what's dy? What dy is, this is dy. So instead of going here, I'm going to go all the way to the tangent. So I'm going to go here. Okay, just like I did before. All right. It was always the distance, the difference between using the tangent or using the actual function. Okay, so this here. This is what we call dy. Okay, so it's the increase. When I increase by dx in the axis, by how much does my tangent increase? So this is a good approximation of this delta y. Do you understand?
Yeah.
But sorry.
Yes, go ahead.
But could we have used the L of X formula that we used before for this problem, or no? We have to use the other one that you gave.
You could have, same thing. You'll get the same thing.
Okay.
You'll get the same thing, exactly. Okay, you understand? You're good? Any questions? Okay, so this diagram I just made is important. Okay. Should we do one more? Maybe we do one more.
Can you just leave the diagram there for 2 seconds
I'm gonna
to
leave it
copy
here.
it?
Yeah, sure. Oh, I messed up here. Okay, so just a quick example, maybe just a computational one. So find the differential. Let me know you're done drawing. So I'm just looking for a good exercise. Okay. This one's okay. So y equals to x squared times sine 2x. So basically, dy will be the derivative of this. So we have to do, of course, a product rule. 2x sine x, 2x sine 2x plus x2 times 2 cos 2x times dx. And that's it. This is my differential. Okay, so it's always dy is equal to y prime times dx, always.
Just to make sure, like dy is equal to y prime.
Dy over dx is equal to y prime, right? You remember at the beginning of the course, when we started derivatives, I told you there's two notations. We said either y prime or we said dy dx. You remember? I said this was like this notation.
So just dy on its own or dx on its own.
So dy on its own is y prime times dx. It is a very, very small value that depends on the very, very small value. Okay? All the mathematical properties still work, except that we're dealing with very, very small values here. Okay? And what's important is the ratio between the two. That's it. Okay, good. Guys, look carefully, 2 seconds. Okay, it's good that you ask this, because if you look here, if I want to find the slope, so let's call this point here Q. Okay, so the slope of PQ, what is the slope of PQ? Well, it's actually y prime. Okay, right? We said we know it's y prime, and it's also equal to, well, dy, right? y2 minus y1 over x2 minus x1. So it's dy divided by dx. Where it's from, you see? That's how you find the slope, right? The rise over the, I don't know what it's called. Run, rise over run, I think that's what they call it. Okay, got it? Question?
So for the second example, dx wasn't given, so we can't do anything. So we just leave it like that?
For the, which example? For here?
Yeah, for that one. That's it? That's the answer?
That's the differential. The example I gave you before was use differentials to find something.
Yeah, because we had dx.
Exactly. So
Okay.
if I would give you the dx, and I would give you the x, then you will be able to find the dy. Exactly.
Okay.
Okay, so in other words, if I'm telling you by how much I advance here, and I'm telling you what point that is, then you could find this point. It ends up being a linearization problem, the same thing. Good? Did you get to the bottom of this? Is there anybody who still have something not clear with this? Okay. Yes, Liam, you good? Vanisha? Okay, good. Okay, so that's it with, that's all there is to say about differentials. Let's go with applications to physics a bit. Okay, so this is also pretty easy, as you'll see. Okay, so you're all taking mechanics now? Yes? Okay. So applications. Okay. So let me think. So let x of t be v, let's say, displacement of an object. Okay, then, so v of t equals x prime. The derivative is the velocity. Okay, and sorry, and a of t, which is equal to v prime of t, which is equal to x prime prime of t, is the acceleration. Okay. Have you seen this in physics? You haven't seen it in physics, no?
Yeah.
Yeah. But have you seen it with derivatives? No. Okay. So let's see it with derivatives. So let me see. I don't know. I'm not an expert in physics, but I know that you have a formula that tells you that the displacement is equal to VI t plus 1/2 times a t squared. Is that possible?
Yeah.
Yeah, you remember this one? Okay. So let's find the derivative. So let's see what do we get. So now that we know derivative, so x prime of t, so this will be VI plus, and this would be AT.
How did you get that?
I did the derivative of both sides with respect to t. Right? VI is a number, it's the initial velocity. Right? A is the acceleration. So if I derive VIT, I just get VI. That's a constant times t. And the derivative of t2 is 2t, which cancel with the 2, so I get AT. Is that okay?
I don't get it.
You don't get it? Who's that?
Alexandra.
Alexandra? Okay, so I'm going to take one step. I'm going to go back one step. So yeah, I'm going to do the derivative of this with respect to t, okay? So you understand the derivative of a number times t is just the number. Is that okay? Alexandra?
Yeah, it's okay.
Okay. Plus, and then 1/2 times a times the derivative of t2 is 2t. Is that good?
Yeah, thank you.
Okay, so I cross out this. And from here I get, so the velocity at time t, basically, or the final velocity, is equal to the initial velocity plus the acceleration times t. So that gives you, I think, one of the formulas that you know, right? You've seen this one, no? Vf equals Vi t, or Vf minus Vi over t equals A. Okay, so we got one of the physics equations from doing a derivative. And if we do the second derivative now, so x prime prime of t, I derive this again, I will get just, this is 0, and this will be just A. Okay, so that works with what I'm saying, that the second derivative is equal to the acceleration. Is that okay? We're going to do examples in a few minutes.
Are we going to do area under the curve?
In calculus 2. Okay, you did this in physics already a bit?
Yeah.
Okay, so right, so the area under the curve is to go the other way, right? If I give you the velocity, you find the displacement. Okay, so for this, then you have to, they need to give you what was the initial position if you want to find the final position. So that's already called a differential equations with boundary conditions, okay, or with initial values, or an initial value problem. So this you'll do in calculus 2. Okay, the other way is a bit harder. Okay, but for now, let's say graphically, and I'm sure you've done this in physics. So let's say I have time and position. Okay, and if you wanted, you had something like this, let's say, I don't know, a graph like this. That's your position over time. And you remember, if you wanted to find the instantaneous velocity, what did you do?
The slope of the tangent.
Okay, the slope of the tangent. I think that you know what the slope of the tangent means now. Okay, so this is let's say the instantaneous velocity at a certain time t1. Well, it will be exactly the slope of the tangent here. This will be v at t1, the slope here. Okay, so I think in what you've been doing in physics is probably you would take a point before and a point after and find like this, the slope of the secant, something you probably know, to try to estimate the slope of the tangent like this, right? Did you do this? I don't know, possibly. That's what I would have done if I didn't know calculus. Okay, but now that you know calculus, you should be able to, from the expression of a position, you could find the velocity at any moment, okay, using derivatives. Are there any questions before we do a few examples? Maybe one or two examples, and then time is going to be up. Okay, so here's an example. So at t equals 0, a diver jumps from a diving board. Yeah, I'm just taking this from a book. 32 meters high. Okay. So his position is given by, so h of t, so the height at times t is equal to negative 16t2 plus 16t plus 32. Okay, so question 1. When does he hit the water?
H is equal to 0.
H is equal to 0, very good. And 2, what is his velocity at impact? So basically when he reaches the floor. Okay, so the first thing we're going to notice is, of course, when t equals 0, so when he starts, t is 0, t is 0, the height is 32. Perfect. We know that the diving board is 32 meters high. Okay, so the equation makes sense with the problem. Okay, so that's the first thing you should notice. So when does he hit the water? So of course, this is like you said very well, h is equal to 0. So when he's on the floor. And so I need to solve a simple quadratic equation. So basically 0 is equal to negative 16t2 plus 16t plus 32. Send everything on the left, divide everything by 2, by 16 I mean. So I get t2 minus t minus 2 is equal to 0, and therefore so t minus 2 times t plus 1 is equal to 0. So either t is 2 or t is negative 1. Okay, of course the time cannot be negative. Okay, unless of course he jumped from the floor and reached the diving board 1 second before it was on the floor and he jumped to the diving board. That's what it means. Okay, but basically after 2 seconds he's going to hit the floor. Questions? Okay. Last question. What is the velocity at impact? So basically we want the velocity in after 2 seconds. So we're looking for v of 2. That's what I'm looking for, because the impact is 2 seconds later. So let's find v of t. So v of t is equal to h prime of t. And so I have to derive this. Okay, and so v of 2, I'm going to replace the 2 in here. So minus 64 plus 16 is minus 48 meters per second. And this is the velocity when he hits the water.